Hi all. In this video, I will aim to walk through some Python code examples and classify their runtime. So just in case you needed a refresher, if you go into this website, you will see here is the BigO complexity chart, and there are several runtimes over here, which can also be used for space complexity. But we will focus on looking at this code and trying to derive the time complexity together. So let's get started. In the first example here, we have a Python code, and well, all of them are Python. So let's go through each step by step. In the first one here, this is a constant. The time is constant regardless of the size of the array, since it will always start at total 0. In the next step, it is also going to be constant. But over here, it will have to iterate every single on each single element. So therefore, this is going to be n, where n here refers to the size of the array. So it will iterate big O n amount of times. In the next for loop, it will always iterate through all the elements in the array again, but this time it is multiplying them with each other. This time it was adding, and then it will simply return both of them. Again, this is done regardless of the size of the array. So what is the time complexity of this example? Well, you can simply go and add every single one here, but you should always take the biggest one or the most dominant one, since these small ones wouldn't affect the time complexity. So the time complexity of this example will be O of n. Well, someone can turn around and say, hey, but there are two here. Well, these are not nested for loops. So when they're not nested, it actually doesn't matter. It doesn't become any bigger. But if we actually want to do it exact, then it would have been 2n plus 3. And if you drop all the constants, it will be O of n. So for the first example, the time complexity is O of n. Now let's look at the second example. And if we look at the difference, here we have a nested for loop. So in the first loop, it is O of n, since it has to iterate each single element in the array. And in the second one, it will also be O of n. The printing is O of 1, regardless of the size, it will print. But for every element x, it will reiterate the same amount of elements for the nested for loop. Therefore, this can be n to the power of 2, which means there is a quadratic relation, which refers to doubling the size of the input will quadruple the amount of running time. So the time complexity of this one is quadratic. Now let's look at example 3 here, and let's actually compare the difference between these two. We do have a nested loop, which is this and this, but the nested loop starts at x plus 1. Here, the nested loop simply just iterated through the length of the array again. So what's the time complexity of a nested for loop that starts at x plus 1? So let's try to figure this out together. So the first one is O to the n, which is a linear relationship. And now let's try to figure out the second one. The outer loop, will run n amount of times. The inner loop will run in the first round n minus 1, in the next round n minus 2, in the third round n minus 3. Since this value iterates, it goes up by 1 on every round, the number of times that this will have to iterate will be n minus 1, n minus 2, n minus 3. And this is actually called the sum of integers 1 through n, which you can look at the derivation more deeply. So there is a way in how to calculate it. We're not looking at the details of this, but since we have the so-called sum of one integers here, then we can derive it to be n to the power of 2 plus 1 over 2. And here we see that if we combine both of these nested loops, then this is the value that we're going to get. If we try to write this separately, it will look something like this. And since these are nested for loops, we multiply them together. Again, if we remove the constants and focus on the dominant values, this will still be a quadratic relationship. So the time relationship here, the time complexity is quadratic. Let's write them out here so we can revisit them all. So this is also quadratic, and this is linear. So linear, quadratic, quadratic. Now let's look at the next example. So how it's similar. So we have some nested loops, but instead we have an if function doing some comparison. Not only that, but the trick is you have two different types of input. You have array A and array B. So starting with the if function, it's going to be constant, as in 0 to 1, since the size of the array will not really affect it. It will still do some if regardless of the size. The length of the array B is the one that actually dominates over the if function. But let's take a step back. So what is the time complexity of array A? So array A, in this case, we're just going to say it's n, as we used to do it before. Array B, though, one can rush and say, well, we can also say n, then the time complexity will be quadratic, but actually it's not, because if this length was 1,000,000 and this would have been 2, then it wouldn't really be quadratic. So we have to denote this with another letter. In this case, we say m. And therefore, the time complexity of this will be n times m. Now, if it happens that n and m are the same size, then we can say this is a quadratic relationship. But no, it's n times m, since we do not have information to tell us what is the length of this array. And that was the trick in this question, is it had two different types of, two different length of array, unknown array, I would say. Now let's look at example 5. You can see that these examples are building on top of each other, getting more and more complicated, or let's say more and more extended. So we see here, that's A, so we're fine with that. And we have explained this now, so we're also fine with that. Now what about this? You can say, well, O, the big O of 100,000, actually no, this is a constant, because it doesn't matter what's the size of the array, this will be executed 100,000 in the range of 100,000 times. So the time complexity, oops, I actually executed it. Stop. So the time complexity of this one is again n times m, or whatever variable you decide to choose for these. Now, how about this code? This code, which reverses the function, reverses the input. So it takes in an array, it iterates only half of the array, we're dividing it by 2, and it does some functions. All of these small functions are actually 1, because time complexity is looking at the size of the array. If I were to double the size of the array, is this increased? Is this quadrupled? What's happening to this? And it doesn't matter if the array is size 1 or, sorry, if it's size 2 or size 2 million, these will still be executed the same amount of times. Well, of course, this here decides that, but these will not have their own time complexities. This will just be a constant. So what about the one up here? One can be tempted to say that it's n over 2, since it's always going to be executed the half amount of the arrays, sorry, half amount the length of the arrays. but the fact that it's half of the array, it still doesn't matter. It's still a linear relation. So we illustrate this as a linear relation. So the output of this is a linear relation. The time complexity, sorry, not the output C. Example 7. So example 7 is not a code, but more of just a walkthrough here. So let's say we have an algorithm that takes an array A, B, C, D. So let's say this is an input of 4 algorithms, or let's say a function, so to say. And we will donate A to be the length of the array and S to be the length of the longest string. So the A of this array can be 3 if it contains 3 elements, and S is the length of the longest string because let's say this has cat, this has Batwoman, this has chicken. So this is donated by S. So how do we get the time complexity of this? I've already put the answer here because this perhaps might be a little bit more complicated than the predecessors. So the first thing the algorithm has to do is to sort out each string. And to sort out each string, it will be the A times S log of S, where S here, if we would focus about here, S is the length of the longest string. So it takes S log S to sort out the length of the string and multiply that by A, which is the number of words in that string. So how long will it take to sort out A? It will be A times S log S. Actually, I haven't explained what this algorithm does. So the goal of this algorithm that it takes array A, B, C, D and sorts them. It sorts each of these arrays individually and then it merges them together. And if we look at the BigO cheat sheet, let's say we will use the time sort or merge sort. Let's say we're going to use the merge sort. The worst merge sort is O(n) log n. So if we just keep this in mind, O(n) log n, which is the time it takes to sort a single string, we simply multiply that by A, which is the length of the array. So an array A will basically take this amount of sort of time complexity in order to sort it. Right, so now we have established that it takes A times S log of S to sort a single input array. And once we have sorted all of them, what would it take to actually sort them in relation to each other? So if we have here, if we have array A and array B, what is the time complexity to sort these? And then what's the time complexity to sort these together? And then finally all of them together. So in the second step here, it has to sort each array in relative to each other, but again, it would be the same as this, but with a slight twist, which is A. And A this time depends on the length of the array. So if the length here is 2, then it will be S log A, while if the array here was 20, then it would be different. And again, we multiply them by the length of the array, which is how many are there. So this is the step 2. And step 3 basically is to put all of these together, and that will be A times S log A of log S, which is basically putting these together, where the first one was arranging an array in relative to itself, and the second one was sorting the arrays in relation to each other and then putting them together. So the time complexity of example 7, which is this. Again, a quick reminder, it takes in several amounts of arrays, sorts the contents of these arrays, and then outputs the sorted content. Example 8. This function basically sums up all the nodes in a balanced binary tree. So if the node is none, it returns 0. That's the best case, but we look at the worst case. Otherwise, it sums node left with the value in the middle and node right. Basically, this iterates over all the elements in the binary tree, so this can simply be established as a linear time complexity. If you had 10, then the time complexity is 10, since it has to iterate through all of them. It's like a for loop, so to say. Okay, example 9. What do we have here? So it gets a value and it checks if it's a prime. Looking again to all of this, this is a constant, this is a constant, this is a constant. Again, if you're asking why are these constants, and that is because it doesn't matter what is the length of n, this will be executed one time only, regardless of the size. If it's 10 or 20, this will all be executed one time. Now here is the interesting bit, which is the for loop. The for loop is always the part where it starts to add some complexity. And here we see it will iterate square root amount of r. So this here, this for loop will execute square root amount of r. And everything else is constant. Therefore, the time complexity of this will simply be the square root of n. Uh, basically, will be the square root of n. So that's the time complexity of this. Again, why is this square root? That's because this for loop has to execute the square root amount of the length n. So if this is 5, what's the square root of that? And this is the number of times this for loop will be executed. Example 10, factorial. So let's take a look at this. Constant, constant. Here's where the fun begins. One can say, oh, the time complexity of this is factorial, because there is a factorial time complexity, which is right here. And I'll come to an end on the namings of all of these. Well, no, the time complexity of factorial is actually not factorial. It is simply O of n. It is a linear. It is a linear time complexity, because if you had 5, then the factorial will be this. But if you all of a sudden increase the n to 6, it simply adds the 6 here. So it's a linear relationship in relation to the time, in relationship to the input size. Fibonacci, example 11. Fibonacci is one of the more interesting ones, and I just Googled here a Fibonacci tree in order to demonstrate this example. So the way Fibonacci works is if you have the value 6, then it needs Fibonacci 5 and 4 to get 6. And to get 4, it needs 3 and 2, and to get 3, it needs 2 and 1. Same here, 5, it gets this and this, and so on and so forth. So if your n value was 3, you only needed 2 values to get Fibonacci of 3. But if you double the input array to 6, then all of a sudden you need all of these. So I'm not going to count them. 16, I think. You will need all of these in order to get f of 6. So a simple double in the size of the input actually increases the number of calculations exponentially. And this is what we see here. It's a multiple recursive call. And generally speaking, when you see an algorithm with multiple recursive calls, you're looking at an exponential runtime. So for this one, it will be O2 to the power of n, which is an exponential time complexity. Okay? Now, this is the same function as here, so it's a Fibonacci, but the difference is there is memoization. I'm not going to go into the details of the memoization, but it's basically saving the calculation as it goes through. So if we look at this here, it calculates F4 once, but it actually calculates it here again. So F4 is calculated twice. F3 is calculated 3 times. So the whole idea of memoization is that it saves the values, so it doesn't have to recalculate it again when it meets the same input. So if the input was F3, then it caches it. It knows F3 is F2 with in addition to F1 will give you F3. So when the F3 comes again, it just, oh yeah, it's in memory. So it doesn't have to rerun it, and it's basically here. It's a dictionary. So if X is not in memo, then do add it in memo and do the Fibonacci sequence. So something super interesting here. I will execute this. So here you can see it took 375 milliseconds, and then I will execute this. And here you see it took only 8 milliseconds. So what is the time complexity for this? It is actually O of n, since it only has to do the calculation one time. it doesn't have to repeat it again and again and again since it uses this caching. Example 13, which is the last one for this video, the power of 2. Basically, this function prints the powers of 2 from 1 through n inclusive. So let's say n here was of the value 4, then it will print 1, 2, and 4, which is basically the powers from 2 up until 4. So what is the runtime complexity for this one? If we take something, perhaps let's not use 10, let's use something that's divisible, so it's easier to illustrate this. So the first time you will have 12, and then if the input is 12, then the power of that will give you 6. It will then call 3. It will then call 1. And these values are actually coming from here. If n1 is less than 1, no, no. So it's basically here. So the power of 2 is basically n over 2. So 12 will be 6. It goes back into the call, checks again, no, no, then please divide it again. You get 3 until you get 1. And then it will return 1. It will come back to the 3 here, and it will multiply it by 2. So 1 will return 1. 3 will return 2, and this will return 4, and 12 will return 8. You can try this for yourself and check. Again, there is a few sources online on the power of 2 if you want to dig into the details, but there it is. As I just said, 3, 8, and 2, 4. But for now, I'm focused on getting the time complexity. So what is the time complexity of this one? And actually, it is the logarithmic of n. And one might ask, what is this logarithm of n? Well, basically, again, I think there are a couple of good charts online here. So if we take a look at this, I actually had an example here. So if you take a look here, if you would double the size of your input data, so if you had 2, it was only 1. If you doubled it, it increased by 1. And if you double it again, it increases by 1. And this is what we're seeing here, because you're actually halving it every time. On every call, it becomes a logarithm of n. I also wrote a short article, or perhaps not so short, on some details. So what is the constant? What's the logarithmic? The whole blog is still work in progress, but I believe you can already go here and start reading and looking at what examples. I also put this graph here. And if you have any questions, just comment on the YouTube video or simply comment down here. And now let's just take a quick look on the graph. So I think we have now covered each example. If we scroll up, we have covered the linear relationship, we have covered the quadratic relationship, we have covered n times m, which is actually not here, but just know this is not everything, but these are the most commonly used. We have, again, square root, we haven't covered that. We have covered the exponential, and we have covered the logarithmic. And n log n in example 7, which was sorting the arrays, which is actually, you still also see it here with the merge sort, which are different types of algorithm of sorting. So we've used this, we have shown examples to most of these. Thank you for watching. I hope it was clear. If you have any questions, please leave them in the comment section below. Otherwise, please subscribe and like the video so I feel encouraged to post more. Thank you.